So hello everyone. Our next talk is given by James Rickards. He will talk about computing with indefinite quadratic forms and quaternion algebras in PARI shaping.
Okay, thank you. Thank you for giving me this opportunity to talk and for running this conference online. It's my fifth Quebec-Maine in a row, so glad I can make it back. So to start, in number theory, I like explicit, concrete things, that you can compute. You can have something, you write a program, you compute it, you study the output, and then you prove conjectures based on the output. So today I'm kind of talking about this interest in relation to my thesis project. So I'm going to start with some background on why I'm interested in quadratic forms and quaternion algebras, describe a few results that came out from the computations, and then describe a PARI package I'm writing to deal with quadratic forms and quaternion algebras. So to start with the background, if you take gamma to be a discrete subgroup of PSL2R, and you take the upper half plane and quotient by gamma, and you equip it with your hyperbolic metric, and you get a nice classic Riemann surface. So a natural object to study on the surface are geodesics. So how do you get them? Well, you take a geodesic in the upper half plane, so a vertical line or a semicircle, and you project down. But more interesting than that are closed geodesics. So the way you get a closed geodesic is you take a primitive hyperbolic element of your group gamma. It has two real roots, and you just form the geodesic attaching the roots. And when you go descend to the quotient, this now becomes a nice closed geodesic. And in fact, this is how you can get all closed geodesics in this fashion. So instead of studying closed geodesics, you can study hyperbolic elements of your group gamma. So people have studied these closed geodesics for years and years. So what I'm studying is intersections of pairs of closed geodesics. So if you take two closed geodesics, you just ask the simple question, well, how many times do they physically intersect on this quotient space? So you can take every intersection, you add out of one, get the unweighted intersection. You can take intersections where you account for a sign of intersection. And so that type of intersection will be defined homologically. And you can do other things where you incorporate arithmetic data coming from intersections. There's a lot of variants you can consider. So I don't study all discrete subgroups. The ones I focused on are PSL2Z, and the other one being if you take an indefinite quaternion algebra over Q, take an Eichler order, and then you take the group of units of norm 1. This gives you a nice discrete subgroup PSL2R, and this is just called the quotient's called a Shimura curve. So these are just some of the most classical objects of study, besides, I guess, congruent subgroups. So kind of some background on why this might be interesting. For PSL2Z, this work relates to some work by Duke, Emoglu, and Toth 3 years ago on the linking number of some modular knots in SL2R quotient by SL2Z. And the case where I take Shimura curves is conjecturally related to some work of Darmon-Vonk on real quadratic analogs of the J function. And this is something I will come back to a little bit later on in a later slide. And very similar to the last point, there's a lot of parallels to the work of Gross and Zagier on the factorization of differences of J values. You get a lot of the same quantities appearing, it just now the discriminants are positive instead of negative. So this is kind of the background, what brought me into this area. So rather than study these hyperbolic elements of these groups, there's actually better interpretations of these elements. So for PSL2Z, the better interpretation is primitive indefinite binary quadratic forms, which I abbreviate PIBQF for simplicity. And the whole point is if you have a PIBQFQ, you can take its automorph, and its automorph gives you a primitive hyperbolic element of PSL2Z. And the roots of the automorph are actually just the roots of Q. So you don't even need really to pass to it. So all this says is that we can formulate the question as you take two quadratic forms that are indefinite, and you have two root geodesics, descend to the quotient of the upper half plane, and then you ask what's their intersection number. So very simple, we start with two quadratic forms and we get some number. And I'll just note that this only depends on the equivalence class of the quadratic form. It doesn't depend on the actual quadratic form. Yeah. Now for Shimura curves, the setup is a little bit more complicated. So we go through what we call optimal embeddings. So we start with an indefinite quaternion algebra B, you take an Eichel order O, and of course you embed your indefinite quaternion algebra into 2x2 real matrices. The actual embedding doesn't matter. So if D is a discriminant, you let OD be the unique quadratic order of discriminant D, and epsilon D the fundamental unit of this order. So an optimal embedding is just a ring homomorphism from this order of discriminant D into the quaternion order. And the optimal part is that it doesn't extend to an embedding of a larger order. So if you just take D to be fundamental, for example, this is automatic. So we're just studying kind of ways to embed the quadratic orders into this larger quaternion algebra. Two optimal embeddings are equivalent if they're conjugate by an element of norm 1 in the Eichel order. And the whole point is, this is how we can construct hyperbolic elements of gamma. So you start with epsilon D, the fundamental unit. When you take this optimal embedding, the image of it is now a unit of norm 1 in your Eichel order. And then once you map that into M2 of R, now you have your primitive hyperbolic element of gamma. So this means that instead of taking these elements of gamma, we can take the inputs being two optimal embeddings. And then we ask, what's their intersection number? By which we mean, if you take the image of the fundamental units, and then you take their corresponding root geodesics, how many times do they intersect on the Shimura curve? And I mean, just a fundamental reason why this is a better approach is optimal embeddings come equipped with discriminants, which give a much better description for kind of the behavior of what's going on, rather than just a 4x4 matrix with some elements. That doesn't really, it's harder to get something out of that. So where do we start? So, well, we have to write programs to compute with quadratic forms, quaternion algebras, compute the intersection numbers, and then study the output. So I chose to do all my work in PARI GP. Personally, it's my preferred language. It's free. The source code is all available online, and it's very powerful. Sage and Magma are also options. My issue with Magma, well, Magma, the nice thing with Magma is they have a lot of stuff to do with quaternion algebras in them, whereas PARI doesn't have that much to deal with quaternion algebras specifically. But Magma is not free, and when I started, McGill didn't have Magma, so that wasn't even an option to me. Well, we had I think a 15-year-old copy on some computer somewhere, but yeah. So PARI GP, just why is there two things? Well, PARI is a C library with, as I said, a lot of tools. And the issue with C is you have to kind of compile your program and then run it. So it can be a bit, if you're just trying to explore, it's not as easy. So GP is a scripting language that allows quick access to all the tools in PARI. So initially I was working exclusively in GP, but as I'll mention later, I'm going back and I'm rewriting everything in PARI because it increases the efficiency by an incredible amount. So, okay, so I'm not really gonna talk too much about all the algorithms, but kind of some of the results that came out of this project. So an initial question is, well, I start with two discriminants, D1 and D2, and I wanna find some interesting examples. So I wanna pick quaternion algebras, I want to find optimal embeddings, and I want there to be intersections. Because if you always find optimal embeddings that don't intersect, that's not that interesting. It's interesting, but you can't really do much with, oh, they don't intersect, okay. So naturally what I did is I took a bunch of pairs of primes, PQ. Well, I fixed D1, D2, took a bunch of pairs PQ, and just computed all the optimal embeddings, all the intersection numbers, and saw if there was something non-zero or not. So you do this over a large box of PQ and you get some list. And when doing this, the list was always, obviously it was finite because there's only finite computation power, but all the primes that appeared were always small. And there's certain primes that were missing. You know, even as P and Q grew large, at some point you stopped seeing any intersections whatsoever. So this was already kind of good evidence towards there being something interesting going on. So kind of the first thing that I found with this was inspired by the work of Gross and Zagier. This turned into the conjecture that if there is a non-trivial intersection, then this following equation has to be true. P times Q divides D1, D2 minus x squared over 4. For some integer x, that's equivalent to D1, D2 mod 2, and it's bounded by the square root of D1, D2. So already from the get-go, if you fix a D1 and D2, there's finitely many choices of x. And then if you factorize this number here, there's finitely many pairs PQ for which there could even be a non-trivial intersection. So this already was very useful in that it really restricted the search space to finding interesting examples. Now at the time, this was just a conjecture, but later on, so this is also necessary, but far from sufficient. But later on, this was refined into a much more precise and necessary and sufficient condition, which has been proven. But even before it was proven, just from the get-go, there was so much evidence for it that, you know, just for looking for interesting examples, it was a very reasonable assumption to do. And the other useful thing is, in this necessary and sufficient condition, when you start adding things like allowing D1 and D2 to not be coprime or not be fundamental, you start to get messier and messier conditions. So having computations to be able to verify that, you know, the theory you did was correct was also very invaluable when the theory involved multiple cases and just got really ugly. So the second computational thing I wanted to mention was this work of Darmon-Vonk. So this was all starting right when I started my PhD. They had this recipe to produce a real quadratic analog to J of tau 1 minus J of tau 2, by which I mean they p-adically constructed some number. It appeared to be actually algebraic, lying in the correct ring class field, and had a very structured factorization a la Gross-Zagier. So the prime factorization was only divisible by primes of small norm of a certain form. Yeah. And this is for now for tau 1 and tau 2 real quadratic instead of imaginary. So the conjecture, part of the conjecture was that the exponents of the primes in their factorization should correspond to intersection numbers on Shimura curves in a very concrete way. So not a statement like they're related, but there's an actual, you take this intersection and you get this exponent. So a very concrete connection between the two. So Jan Vonk had written these algorithms to compute their analog, and I had my algorithms to compute these intersection numbers. And we played around with a bit, found what appeared to be the correct intersection number, and we did a big test. So I took D1 to be 5 and 13, and I took D2 to be every discriminant up to 1,000, computed every single possible non-trivial intersection for each pair of discriminants. So for every pair of discriminants, every single quaternion algebra for which there could be non-trivial intersections, computed all the optimal embeddings and all the intersections, made this into a big document, turned out to be almost 600 pages. And it took about a week to do at the time. I think now it would only take maybe an hour or two because the algorithms are much more efficient. But anyway, so Jan took a look at this data, and in every case we could find the data matched perfectly. So this was really nice evidence. We had two very different constructions, completely unrelated and written completely different programs, and they'd managed to output the exact same numbers, which felt like extremely strong evidence towards this whole theory being correct. So where does that lead me now? Well, over the time I realized that a lot of these methods could be useful to other people, just because there isn't much in PARI specifically for dealing with quaternion algebras And there's some stuff for quadratic forms, but just a few things. So my project for this summer, since I suddenly had a free summer, was rewriting everything in PARI just to very clean it all up and make it more efficient. And just rewriting things in PARI automatically increases speeds by often about 10 times. I've had some algorithms increased by 100 times because it became a little more efficient in other ways. So everything's going a lot faster now, although it was fairly fast before too. In addition, because this is not, I'm hoping other people might find this useful. So I'm writing user manuals for how to use the entire project. So I don't just put the algorithms out there and good luck trying to figure out how, but how to use everything involved. Because I think, well, it's also very useful for me, because once you get enough methods, you forget how some of your own methods work. And I'm continuously updating my package on my GitHub account. The current live version is version 0.3. The reason it's 0.3 and not 1 is because this is still a work in progress, and there's still a lot more that I want to do, but I haven't yet done. I still have algorithms I have in GP that haven't yet been translated over to PARI. So this is just a quick documentation excerpt. Too important, right? So what algorithms have I implemented and what are planned for this package? Well, computing the narrow class group associated to a discriminant D in terms of binary quadratic forms. This is something that's in PARI GP, but there's a slight twist. And I couldn't seem to find it exactly in GP. You could either compute the full class group or the narrow class group if the discriminant was fundamental. But if you're in a situation with a non-fundamental discriminant for which the narrow class group is twice the class group, this didn't actually seem to be in PARI GP, or at least I couldn't find it. So there's this. So as I haven't really specifically mentioned it, but most of my work has been with indefinite forms and indefinite algebras. So there's a lot of stuff to do with indefinite quadratic forms. So there's not just a unique reduced form, but a unique cycle reduced forms, left, right neighbors. If you're familiar with what's called the Conway topograph, there's a lot of data for computing the Conway topograph, the Conway rivers, etc. And another thing that was useful when I did the quaternionic stuff was finding general integer solutions to a 2-variable quadratic equation. So there's actually, if you want to solve this equation, there's actually finitely many families of solutions that you can describe explicitly. So having a method that does this automatically for you is implemented. I will note that in GP, if D equals E equals 0 and N is a prime, there's a method to find one solution. But this sometimes you want to find all the solutions, and oftentimes N might not be prime. So yeah. So for quaternion algebras, there's a bit more to do. So the basics: initialize the quaternion algebras, maximum orders, do all the basic things you add, subtract, divide, multiply, conjugate, etc. So none of those are very interesting. But more interesting is computing all optimal embeddings of a discriminant into a given Eichler order. I didn't mention this, but there's an action of the class group on these optimal embeddings. So sorting them by this action of the class group. And then each class group orbit is called an orientation. So sorting them by orientation and action. And then obviously computing these intersection numbers. Currently, I have 2 distinct methods for computing them in that each have their advantages in different situations. Yeah. So just briefly, this is some sample output. I'll just run through it quickly. In the first slide, I initialized a quaternion algebra, ramified it 2 and 7, and a maximum order. The next slide, I compute what discriminants can I embed in this quaternion order, because you can't embed every discriminant. The third line, I decide to embed 61. The fourth line, I decide to embed 2021. Unfortunately, you couldn't embed 2020 in the one I chose. So 2021 was the next best thing. So 2021 has class group 6. So for every orientation, there's actually 6 embeddings. And then I just computed their intersection number via both my methods. And in each case, they had 12, their unweighted intersection number is 12. So this is just some example output. End to end, what are some planned algorithms that I haven't implemented, but I'm working on? Well, computing fundamental domains for Shimura curves. So this is an algorithm that is in Magma. So I'm following a paper of Voigt with some optimizations by Paj. And I have a partially working prototype in GP, but it hasn't been transferred to PARI. And there's a few bugs in certain cases, so that's working on. Solving the principal ideal problem for indefinite quaternion algebras. So if you have an ideal, it's principal. But finding that generator explicitly turns out not to be a very easy problem. So there's an algorithm due to Paj that I plan to implement for this. This will improve my computation of optimal embeddings, which currently is very naive and not very efficient, but it's not a bottleneck, so it wasn't a priority. And just continue to implement other basic methods, because I've been always focused on methods useful to my project, which doesn't include all methods that are useful. So thank you for your attention, and